Now that we designed our special purpose implementation, the finite state machine, to solve this problem, let's begin designing our general purpose computer to solve the same problem. Every computer has inputs and outputs, and this one will have the exact same input and the exact same outputs as our previous implementation. We need to connect our D-out outputs to something, and what we'll connect it to will be a register. Recall that a register is a sequential building block that allows us to load the register with a new value when its load line is a 1 and when we have a rising clock edge. When those two conditions are met, the value in the D input bus will be loaded into the register. This register also has an asynchronous low true reset line that will allow us to clear this register at power up. Remember that we can change the behavior of a computer by changing its program, which means that we change its instructions. Instructions are going to be stored in memory, so we need a memory device on our computer. We have no idea yet how many locations that we're going to need for this memory, or how wide this memory is going to be, how many bits per location we need. That's going to be determined by how large a program that we store in this memory and what our instruction format will be. So our memory contains instructions. Well, what exact instructions do we need? We can start making those decisions by writing some code that we intend for this computer to execute in order to solve this problem. This code will be in pseudocode, which means that it doesn't intend to represent any particular programming language. So we'll start out with a label called start, which will be the beginning of our program, and our first statement will be an if statement. And this statement will say if loc is equal to true, go to local, which means that if loc is equal to a 1, we're going to jump to this place in the program. So if loc is equal to 1, we'll jump here, and then we'll start executing these statements in sequential order. The first statement, d out equals 8, is going to cause an 8 to appear in a d out bus. Then we're going to move a 5 to the d out bus, a 6 to the d out bus, and display a 1 on the d out bus. Then we're going to execute a go to statement, which is going to cause control to jump back up to the top the program at this label and begin execution again. If loc happens to be a 0, then we will not take this jump, and instead we will simply execute the next statement, which in this case will copy a 3 to the D out output bus, then we'll display a 2, then we'll display a 4, display an 8, display a 5, display a 6, display a 1, and go back up to the top. Notice that this program only looks at the loc input at this point in the program. If loc changes anywhere in here, we're already on our fixed path to displaying either all 7 digits or only these last 4 digits. And looking at this program, we have exactly 3 different types of instructions that are represented in this program. One type of instruction is an output instruction in which we're causing a digit to display in our output bus. So this will be called an out instruction. Another type of instruction is a go to statement, or a jump unconditional, in which we're always going to jump to some new place in our program. So we'll call this particular instruction a jump instruction. And it's an unconditional jump. We will always, if we execute this instruction, we will always go to this location. The third type of instruction that's actually in this program is a conditional jump. This conditional jump, if loc is a 1, we will go to this label. However, if loc is a 0, we will not go to that label, and we'll simply execute the next instruction that follows. So this is going to be called a jump conditionally, based upon the value of the loc input. Our next decision is, how are we going to actually store these instructions in memory? Well, one thing we could do is we could store each character for this text as an ASCII code in memory, and have our computer try to interpret these ASCII codes as instructions. That would mean that each letter would take a minimum of 7 bits. And while we could do that, it would be very inefficient to do that because of the fact that this has many characters representing this instruction, this has many characters representing that instruction, and so forth. While that would be a human readable form of storing the program in memory, we would actually like to have a much more efficient way of storing this program. What we need is a very efficient binary encoding for our instructions. Typically, instructions are encoded using multiple fields, and what we're going to use for our instructions is going to be two fields. One field is going to be called the operation code, and it's going to specify what the instruction is. The other field is going to be called the data field, and it's going to be the data needed by the instruction. So how many bits do we need for the opcode? Well, we have 3 instructions. That means that we need a minimum of 2 bits because 2 squared equals 4, so that means that we could have actually up to 4 instructions using a 2-bit opcode field. Now that we know that we need 2 bits for the opcode, what's going to be our encoding for instructions? Here we've chosen a 0 for the jump, a 1 for the jump conditional, and a 10 for the out. We could have chosen another encoding for these instructions, but we did this on purpose. These 2 instructions are related. They're both jump instructions. While this instruction is not a jump instruction. When we build a digital control for this, we'll be able to see that just by looking at this bit, if it's a 1, we know it's an out instruction. If it's not a 1, we know it's going to be some form of a jump instruction. So now that we know what our opcode field looks like, let's move to the data field. The data field for the out instruction is pretty obvious. It's going to need to encode the digits 0 through 9, which means that we need a minimum of 4 bits to do that binary encoding. A 0 will be represented as 000, a 9 will be represented as 1001. What about the data field for the jump conditional instruction and the jump instruction? For simplicity, we're initially going to keep this field the same width as the data field for our out instruction, and what this field represents is going to represent a location in memory that we're going to jump to. In other words, it will represent the address of the instruction that we're trying to jump to. By using only 4 bits, this is going to limit our memory to only containing 16 locations. It will also limit our program to only being able to contain 16 instructions. The total width of our instruction, which is going to be how many bits we need per memory location, is going to be 2 plus 4 is going to be 6 total bits. So this gives us a very efficient encoding for our instruction. Each instruction will take 6 bits. Let's take our pseudocode program and rewrite it using the instructions that we just designed. Our if statements become a jump conditional, where the operand of the jump conditional statement is the label that indicates the instruction that we're going to jump to if the condition is true. In this case, the jump conditionally checks the loc input, and if it's a 1, we will take the jump. If the jump is not taken, if the condition is false, then we will simply execute the next instruction. The DOut assignments are replaced by out instructions, in which out 2 says to output the digit 2 on the DOut output bus. Our goTo statement is replaced by a jump unconditional. The operand of the jump statement is a label that indicates where we're going to unconditionally jump to. A program that is written using the native instructions of the computer is called an assembly language program. So we need to place our assembly language program into memory. In order to do that, we need to convert our assembly language instructions into their binary representation. This binary representation is called machine code. And looking at the JC instruction, its opcode is a 0-1. The operand of the jump instruction is going to be the address of where we're going to jump to if this jump is taken. That happens to be this instruction right here, which is sitting at location 4. So that means that this 4-bit field right here is going to equal to a value of 4, which represents the address of the instruction that we're going to jump to. For an out instruction, its opcode is a 10. Its data field is going to be the digit that we're trying to output. In this case, it's a 3, and a 3 is encoded as a 0011. Similarly, in out 2, the out opcode is a 10. The 2 is encoded as a 4-bit value, 0010. Finally, the jump instruction, how is that encoded? The opcode is encoded as a 00. The start label is going to be the address of the instruction that we want to jump to. The address of start happens to be location 0, so this 4-bit field is going to be encoded as 000. Note that each memory location contains exactly one instruction, and that this particular program contains exactly 9 instructions. Our memory actually has room to contain a 16 of total instructions, so we could write a larger program if we wanted. Let's return to designing the hardware for our computer. We now know some more facts about our computer. For one thing, we know the size of our memory. We know that it's going to contain 16 locations, and each location is going to be 6 bits wide. That means that this data bus out here is going to be 6 bits wide, so the index is going to be 5 down to 0. Since it contains 16 locations, we need an address bus that's going to be 4 bits wide. That means that this is going to be 3 down to 0. We need something to drive this address bus with. The address bus is going to contain the address of the instruction that we're going to want to fetch and execute. To drive this address bus, we're going to use a counter. Recall that a counter is a sequential building block. It's like a register, but it has the additional capability of being able to increment. Typically, this address bus will contain a value. Let's just say it'll contain 2. And typically, we will increment this counter in order to actually fetch the next instruction in memory. So we would increment this to a value of 3. However, sometimes we will want to load in a non-sequential address using the load line, and we'll need to do this for the instructions jump and sometimes jump conditionally. This DN bus here is going to be the same width as our output, so it's also going to be a 4-bit bus, and this index is going to be 3 down to 0. This particular counter is present in every computer, and it has a special name. It's called the program counter or instruction counter. To complete our design, we'll need some control logic, which will determine the sequence of operations that happens on the control lines for our various elements in our computer. For example, we'll need to specify when this load line's a 1 for the D output register. We'll need to specify when this load line's a 1 and the increment line's a 1 for our program counter. This is going to be combinational logic, and it's going to be based upon the opcode of our current instruction that's being fetched out of memory. Recall that our opcode is in the top 2 bits of our memory bus, so our memory bus is going to bits 5 and 4 will be the 2 bits of our opcode. This control logic will also make decisions based upon the current value of the loc input. So let's start designing this combinational logic. First thing we're going to do is concentrate on the combinational logic that drives this output load line. When this output load line is a 1, we're going to load in this lower 4 bits of this memory bus into this register, and it's going to appear in this output data bus. So when do we want to do that? We want to do that when we have an out instruction. How do we know that we have an out instruction? We know that we have an out instruction when the upper 2 bits of the memory bus, which is our opcode, is equal to a 1, 0. When that happens, we want to take the lower 4 bits of our instruction, which will be whatever our digit is, perhaps 2 or 4 or 7, whatever, and that's going to load into this output register. We'll describe this combinational logic using this VHDL code, and we'll also show this in gate form in a second, which will say our output load is going to be a 1 when our opcode field is a 1, 0, else it will be a 0. Now let's talk about the combinational logic to drive the PC load line. We want this line to be a 1 whenever we desire to load in a new value to our program counter that's not going to be an incremented value. Well, when do we want to do that? Well, we want to do that whenever we have a jump instruction or whenever we have a jump conditional instruction and when loc is equal to a 1. Let's write this in VHDL. So our PC load line is going to be a 1 whenever we have a jump instruction, whenever our opcode is 0, 0, or whenever we have a jump conditionally instruction, a 0, 1 for an opcode, and our loc is equal to a 1, else it's going to be a 0. Well, if we're not loading, then we're going to be incrementing. So the easiest way to write the logic for the increment line is say that if we're not loading, we're incrementing. So PC increment is simply going to be the not of PC load. Now let's write Boolean equations for these output lines. So the output load, remember we want it to be true when we have an output instruction, which is an opcode encoding of 1, 0. Recall that for our opcode encoding, this bit right here, the most significant bit of the opcode, is only a 1 whenever we have an output instruction. So we can just use that as the control line for the output load line. For the PC load line, we want it to be true whenever we had a jump instruction, which meant that both these opcode bits here were 0, or whenever we have a jump conditionally, which meant that this bit right here is a 0 and this bit right here is a 1, and also whenever the loc input was a 1. Finally, the PC increment is simply the inverse of the PC load line, is a not of PC load. This slide shows the final hardware for our computer. These gates right here implement the Boolean logic on the previous page. Notice that our load true reset line here is tied to the asynchronous reset line of our program counter and also to our output register. This means that at power up, when we assert reset, we're going to fetch our very first instruction from location 0 because this register will be set to 0. Also, our dout bus at power up reset will contain the value of 0. This timing diagram shows the execution of our program in our computer. Initially, our reset lines asserted low true. That means it's going to clear our program counter to 0 and our dout register to 0. Remember, the program counter contains the address that's of the instruction that's currently being fetched and executed from memory, and our first instruction at location 0 is going to be a jump conditionally 4. So that means that during this clock cycle, we're fetching and executing the jump conditional 4 instruction. Because our loc input during this clock cycle is a 0, we are not going to jump to location 4. We're simply going to increment the program counter to the next address, which is going to be location 1, and we're going to fetch and execute the instruction out 3. This 3 is going to be loaded into our dout register on that rising clock edge, or our dout bus will then show a 3, and our program counter will increment to location 2. We're going to fetch and execute the address, the instruction at location 2, which happens to be an out 2, which means that this 2 is going to appear on the dout bus on that rising clock edge at that point. During this clock cycle, our program counter is at location 7, which means that we're executing the instruction out 1. So this 1 is going to appear in a dout bus after this rising clock edge, so there's going to be a 1 here. At this point, we're then going to fetch the instruction from location 8. Location 8 is going to be a jump to 0, which is our looping back to the beginning of our program. So at this point, our program counter is going to be loaded with this value 0, and we're going to fetch our jump conditional instruction again. So during this instruction right here, we're going to be fetching, executing jump conditionally 4. Notice that our dout bus here is stuck at 1 as we're executing this jump 0 instruction, as we're executing this jump conditionally 4 instruction. At this point, when we're executing the jump conditionally 4, we're going to look at our loc input and see that our loc input is equal to a 1. That means that we need to take this 4 and we're going to load that into our program counter, causing a jump to the instruction at location 4. So at this point in this clock cycle right there, we're going to be executing the instruction at location 4, which happens to be an out 8, which means that this 8 is then going to appear after this rising clock edge on the dout bus, and our dout bus finally changes from a 1 to an 8. Let's see how efficient our computer is at outputting the digits of this number. We have 1, 2, 3, 4, 5, 6, 7 digits to output. Let's count the number of clock cycles that it took to output this complete number string before we started outputting the second number string. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 clocks before we started outputting our next number string. Recall that our finite state machine only took 1 clock per digit. Here, in some cases, we're taking multiple clocks per digit because of the fact we have these overhead instructions, jump 0, jump conditionally, and 4 that we're executing. So in comparing our two implementations, our finite state machine implementation only took 70 flip-flops plus a very small amount of combinational logic. The small amount of combinational logic will mean that it will operate at a very fast clock rate, much faster than our general purpose processor implementation. However, the drawback is that this finite state machine implementation can only do one number sequence. In order to do another number sequence, you would have to change the combinational logic, which means changing gates, changing wires. Our general purpose processor implementation required many more gates than the finite state machine implementation. And because the logic is more complex, it will execute at a slower clock rate than this finite state machine implementation. However, it's general purpose in that it can implement any number sequence simply by changing the program. And memory contents are easy to change. We can change memory contents without changing any hardware. There are many applications that are much better suited for implementation by a general purpose digital system such as a computer instead of by dedicated logic. We introduced a lot of new terminology in this lecture. Let's review some of that. An address bus is the input bus in our memory device that specifies the location of data that we want to either read or write from that memory device. A data bus is in reference to a memory device is the input-output bus to that memory device. The program counter in the computer is a special register that's in the computer that specifies the address of the next instruction to be executed. An instruction mnemonic is the ASCII representation or a human readable form of an assembly language instruction such as out4. Machine code is the binary representation of that instruction. In this case, the machine code for out4 was a 0-1. That was the opcode for that instruction, and the data was 0-1-0-0. That represented that field right there, the data field. Continuing our vocabulary review, the operation code is the part of the instruction, the part of the machine code that tells what the instruction is. For example, for the jump instruction, the opcode was a 0-0. Assembly is the process of converting instructions from their human readable form, such as this, to their machine code form, such as that. Disassembly is the reverse process. Given some machine code, convert that to its human readable form. We talked about the fetch execute cycle. This is what processors do all day long. They fetch instructions from memory and then they execute it. So our number sequencing computer shares many things in common with modern processors in that it has control, it has registers, it has memory, it has I/O, but it also differs from modern processors. Let's talk about those differences. Our number sequencing processor had 4-bit wide registers. Commercial processors could have registers from lists that range from 8 bits to 128 bits depending on the processor. Our processor only had 2 registers. Commercial processors can have lots and lots of registers, dozens of them, some of them general purpose, some of them special purpose. Our number sequencing processor only had 3 instructions. Commercial processors can have anywhere from tens to even a few hundred instructions of all different types. Our number sequencing processor could only address 16 memory locations. High-end commercial processors can actually address billions of memory locations. Finally, our number sequencing processor could be implemented in just a few tens of gates. High-end commercial processors can take hundreds of thousands to even millions of gates to implement. This concludes our lecture on topics in Chapter 2. This slide contains study points for when you review the material in this lecture.